confidence intervals for mean and the proportion distribution. So finding confidence interval for a proportion. And as always, your sample is simple random. Population is at least 20 times as large as the sample. The items in the population are divided into two categories. And the sample contains at least 10 individuals in each category. Then your confidence interval, as before, proportion minus your error to the proportion plus your error. Where the error is z alpha over 2 times the square root p hat times 1 minus p hat all over n. As a refresher, common critical values. Again, alpha is 1 minus your confidence level. %90 confidence gives us a critical value of 1.645. 95% confidence is 1.960. 98% confidence, 2.326. And 99% confidence, 2.576. So that's a refresher from last week. Sample size. Sample size required for a confidence interval for p hat with a specified margin of error E is either the ceiling of p hat times 1 minus p hat times the quantity z over e squared. That is if p hat is known, so you already know your sample proportion. If you do not know your sample proportion, it is the ceiling of 0.25 times the quantity of z over e squared. That 0.25 is found to be the maximum sample size. A market research firm is hired to estimate the percent of adults living in a large city who have smartphones. 500 randomly selected adult residents in the city are surveyed to determine whether they have smartphones. Of the 500 people surveyed, 421 responded yes. Using a 95% confidence interval, missed a lot of words in there. That's better. Using a 95% confidence interval. Compute a confidence interval estimate for the true proportion of adult residents of the city who have smartphones. All right, first things first. Simple random sample. Generally, we're going to skip that check because it's always going to be a simple random sample. Is the population at least 20 times the sample size? So what's 20 times 500? Oh dear.
100,000?
10,000. 2 times 500 is 1,000 times 10. Is 10,000. Does a large city have at least 10,000 residents? Yeah. That's way more than that, generally speaking. Large cities can be up in the millions. So, okay, that condition can be safely assumed. There are 2 categories, yes or no. Perfect. Are there at least 10 respondents in each category? Yes. There's 421 in the first category. 500 minus 421 is greater than 10. So all 4 conditions are satisfied. Slide. We need p hat. All right, so what's the proportion we're looking for? They own or they don't own? What was it? Well, that's why I'm asking, what proportion are we looking to estimate? That they own a smartphone or that they don't own a smartphone? So then the 421 is the statistic we would use.
Yeah.
Right, you have to be careful. I could say 421 responded yes, and then ask proportion of those who don't own.
I know, that's what it is.
Right, so then you want to be able to do 421 over 500 with your p hat.
Oh. So.
Right, so p hat is 421. Oops, I hit the wrong button, which means you're going to load. You can go away.
6.
It's 421 over 500. I'm going to leave it like that for now. We also need a sample size. That was easy, right? It's 500, they told us. We need our critical value.
And then
95% confidence, 1.96. And our alpha is 0.05. Margin of error. So z alpha over 2, square root, p hat times 1 minus p hat over n. What's 1 minus the p hat?
negative 14.
I don't want a decimal. Keep it as a fraction. So 1 minus p hat.
Yeah.
You forgot that it's a fraction. You did 1 minus 421.
0.842.
I don't want decimal.
You want to keep it as a fraction?
I want it as a fraction. I don't want to round until the very end. Reduces error.
Is it all, is that 0.1?
79 over 500. I don't know why I wrote minus there, and that should be times. That's better. This is fun. We have a 500 cubed in the denominator. Oops. All that over 500. .032.
How would you guess the 1
Hmm?
Guess the 1
1 minus p hat. P hat's the 421 over 500. It's really a question of how many decimals do I want to go out to for proportions? 4? I'll stick with 4, I think then. So it's .03, still be .032. .032, but I'm going to add an O on it as well. As a general thumb, you don't want to round until the very end of your calculation, which is why I kept those as fractions instead of decimals. The more rounding you do throughout a problem, the more error you accumulate in your calculations. That would be the confidence interval, so now I'm just going to write them as actual decimals. Confidence interval 0.8100 to 0.8740.
you have to do 4 decimal point answer?
That's what I'm gonna stick with, because it's proportions. So I'll stick out the 4. What's the interpretation of that confidence interval?
Quick question. So I got the answer for your last one. How did you get the first one for the top one?
What do you mean
Like the
top
last,
one?
like I got the 0.87, like 39 rounded, but how did you get 0.8100?
The 421
It's
over
the
500
421 over 500 minus the 0.0320.
Okay, thank you.
So what is the interpretation of that interval from last time?
Point
95% confident that the proportion of these city residents who own a cell phone is somewhere between 0.8100 and 0.8740.
Can you show me for the 79? I'm trying in here, but I don't know sometimes.
All I did was 500 minus 421.
Oh.
Because 1 as a fraction with 500 as a denominator is 500 over 500.
Thank you.
Oh, well. Just the same thing, just different formulas because it's a different statistic we're looking at. For a class project, oh, speaking of projects, for a class project, political science student at a large university wants to estimate the percent of students who are registered voters. Surveys 500 students, finds that 300 are registered voters. Computing 90% confidence interval for the true percent of students who are registered voters, and obviously always wants to interpret. So check your conditions. Purpose of this class, you can always skip the simple random sample. It will always be a simple random. Is the sample at least, or is the population at least 20 times the sample? So again, 500 times 20 is 10,000. Is it safe to assume that a large university has at least 10,000 students registered?
Yes.
I'd say yes. It's not going to be this on the same scale as a city, but you know, I'd say a large university probably has at least 10,000 students. Are there 2 categories?
Yeah.
What are the 2 categories? Are there at least 10 in each category?
Yes.
All the conditions are satisfied.
So it's valid.
I actually want to go back to this one real quick. So I'm going to check how to do it on the calculator.
Good question. For the question after this one, after the one that we're doing now, multiply 500 by 20. Why is that?
One of the conditions is your population is at least 20 times as large as your sample. So again, you can do confidence intervals for proportions on your calculator. Again, for the one that I'm using, the one I recommend, Menu, stack, confidence interval,
Wait, which one? Oh.
and 1 proportion Z interval. Right, you'll deal with 2s if you take stat 2, I'm sure. So number of successes.
That 300.
I'm doing the previous problem
Oh.
right now, 421. Sample size, 500, and the C level, 0.95. Hit OK. And there you go. So again, a good way to check. All right, now back to this one. What is the proportion we're looking for? We only have 2.
503.
Number of students who are registered,
Yeah.
which means our p hat is going to be the number of students registered in the sample. Which is what?
300.
So the portion will be 300 over 500. This one I actually can put it as to a decimal because this will be a nice decimal. It's 3/5, which is 0.6.
Zero 0.636.
That's not right. It's 3. It's
Oh, it's just 0.6. Yeah.
it's
sorry.
3 over 5, which is 0.6.
Yeah, sorry. I was looking at the C upper.
Write this out. What is our alpha? That's Z. I don't want Z yet. What is alpha? (0.1). 9% confidence, so we have a 10% significance level. Which is, yes, a critical value of 1.645.
Professor, how did you get it alpha considered X?
Alpha is your significance level. It's 1 minus the confidence level. First line.
It's 0. Yeah. It's 90%.
And sample size is obvious.
500.
Margin of error.
0.036.
1.645 times the square root, 0.6 times 1 minus 0.6, all over 500.
0.036. 0.0360.
0.0360. Confidence interval 0.6 minus that. Point 564. Is that right?
56. You right. 0.5639, but you rounded up 0.4.
0.564. And then 0. Adding's easy. I'm gonna just not put zeros for the sake of space.
So I have a question. So X will always be like 0.1. I mean, sigma,
Alpha?
alpha, yes,
No, alpha depends on the confidence level.
okay, sure.
It's always 1 minus the confidence level.
Okay.
What is the interpretation? Yeah, so 90% confident that between 56.4% and 63.6% of these university students are registered to vote.
So, I'm looking into this part, I keep trying to understand it. What would be an example of one minus the confidence level? Like, I'm like super in my head right now.
So what is the confidence level here?
It was 90%.
90%, right? 90% as the decimals what? What's 1 minus 0.9?
Okay. All right, I see. All right, I got it.
That's your alpha.
I'm sorry.
For the most part, what your critical value is going to be one of the 4 that was listed. I only read out alpha in the rare case that you get one that's not 90, 95, 98, or 99.
So you always subtract 1 minus 0.9, you saying?
Whatever the confidence level is. And remember, if your critical value, it's out, you want to find the z value such that alpha over 2 is the area to the right. So in this case, alpha is 0.5 or 0.1. So alpha over 2 would be 0.05. So you want the z-score that has an area of 0.05 to the right of it. The easiest way to do it from your chart is look for the z-score that has an area of 0.05 to the left. That'll be a negative z-score. Take its absolute value. And you'll find on your chart that's you're going to have 1.64 and 1.65. Because you're not going to find exactly 0.05. So then we just take the average of the 2, which is the one right in the middle, 1.645. Mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers age 50 plus should the company survey in order to be 90% confident that the estimated proportion is within 3 percentage points of the true population proportion of customers aged 50 plus who use text messaging on their cell phone? I am about to age myself. Who remembers the phones that you had to push a number multiple times to get your desired letter? I am so glad we don't have to do that anymore. Because then the screen was so freaking small, you're like, Of course, this freaking iPhone, my fingers are too fat. I always hit the wrong damn letter. So I'm always misspelling stuff. Oh, look, the D and the F are next to each other. I guarantee you I misspelled duck a few times. So we want a sample size. Remember what the sample size is. You have 2 options for sample size. If you know p-hat, or if you don't know p-hat.
So right now it's unknown.
This on,
Yeah, we don't know p-hat, do we?
Yeah, it's unknown.
So we're going to be using the second.
Would it be 50 plus?
Now 50 plus is just our population.
Okay.
Right, so when we go to find the sample, we're going to make sure that they're aged 50 plus.
Okay.
We're taking a sample only from people aged 50 or older. What is E? What is our margin of error?
2%.
Write that as a decimal.
0.2.
Not small enough.
That's 0.1.
That's 30%. 0.03 would be 3 percentage points.
And how did you get 0.03?
They told us right here within 3
Oh,
percentage
3
points.
percentage. Okay, thank you.
Right. I think you gave me the alpha.
Yeah.
0.1. That is our alpha. Right. Why? Because they said we want a 90% confidence. Then what is our critical value?
The 90%.
That's confidence. What's the critical value for that? 1.645. That's everything we need.
this one,
Alright, so I'm gonna show you two ways. First is obviously just to do that.
In the previous slide, the E was on the bottom. Is it supposed to be flipped?
It's possible I screwed it up.
It's-
Yep, no, my dyscalculus stuff.
It's 83.
It should be Z over E. I need to change this. That's the ceiling of 751.6736, one repeating.
Oh, so you wasn't supposed to put 0.03?
No, I mixed it up. It's supposed to be Z over E, not E over Z.
Oh, okay.
Point 67361 repeating. 6, 7. Oh, fucker. Remember from last time that interpretation for the ceiling, what does that evaluate out to? So that one is repeating. But what would this ceiling be? 752, it always rounds it up. We'd want a sample size of at least 752. You could go higher. Other way you could do it, if you have the calculator I recommend. This has the ceiling function built in.
What did you just do?
I just spelled out ceiling.
I'll just spell it out.
Otherwise, you have to go into the menu, which is this dictionary here, and scroll through all the options. Because I don't think there is another place for it. And it just gives it 752 right off the bat. But it doesn't matter, right? Because all you do is look at what it gives you and round it up as the ceiling. But I am fairly certain that TI-84, the TI-83 does not have the ceiling function. And I know for a fact scientifics don't. I don't even know if the TI-89 has one. Might. But either way, we get a sample size of 752. yet to do hypothesis testing.
And this is like introducing for project 3, right?
I got stuck in my project.
Yeah. Project 3 is going to be it's confidence intervals for mean and then hypothesis testing.
I mean, give me the.
This is the last thing we do, by the way, this semester, hypothesis testing. We look at hypothesis testing for the mean and proportion only. So hypothesis tests are used to make decisions or judgments about the value of a parameter.
So this section
What
B
is
is
that?
Is it? Yes. Hmm? Well, next week we don't meet
That's with
because
this.
it's Thanksgiving. The week after that we do the final lesson, and then the week after that's the final. I'll mention it at the end. Yes, you do. It follows the Friday schedule. So if you have Friday courses, you actually do have classes next Wednesday. It's so weird the way they do it. I don't get it. But I will mention it at the end.
Will you give us extra bonus point too? Like, or do we have a review trip or no?
There will be. We'll do that on the last day. Not the exam, the week before the exam. We finish up and then I'll do what I did before. I'll answer that at the end. So when you do a hypothesis test, you have two statements. You have what's known as the null hypothesis, H naught, which is the hypothesis to be tested, and it is assumed to be true. Then you have the alternative hypothesis, H sub A or H sub 1. If I accidentally write like H sub 1, it's the alternative. This is the hypothesis considered to be an alternate to the null. And it's what we believe might actually be true. And there are three types of alternative hypotheses, which will be discussed in a couple of slides. So since a sample statistic is being used to make decisions or judgments, it is possible that the conclusion we reach is reached in error. Or in other words, we draw the wrong conclusion.
Is this a specific sign for error or no? Is it a specific sign? for this or no?
What do you mean?
Like error, like you know how you just gave us the null hypothesis is like H and little L, and alternate hypothesis is H little n. Do error have one?
Two types of error. Type 1 type 1 occurs when we reject the null hypothesis when the null is actually true. Type 2 error, not rejecting the null when it is actually false. The probability of making a type 1 error is called the significance level. We keep it denoted as alpha like we did with the confidence intervals. This alpha is used as a basis to determine the rejection region. Since it represents the probability the test statistic will fall in the rejection region when in fact your null hypothesis is true. The rejection region is determined not only from your significance level, but also by the form of the alternative hypothesis. There are three forms: a right tail, a left tail, and a two tail. Rejection region, set of values for which the test statistic leads to rejection of the null. Beginning and ending of the rejection region are called the critical values. That sounds familiar. Right, test statistic is the statistic used as a basis for deciding whether or not H naught is rejected. So this would be a left-tailed test. Right, notice the rejection region is the left. This would be a right-tailed. And this is the two-tailed. Now for the actual process. Starting, as I said, we do hypothesis tests for two, population mean and population proportion. They're not the only hypothesis tests, though. Remember when we did regression? Right, we did the regression line. We found the coefficient, the correlation coefficient R. That is actually a hypothesis test. Which is why I hate that everyone wants to do it before we do hypothesis testing. Because you actually use R, I think you use R squared to determine whether it's a good, whether you can approximate it linearly or not, whether there's a linear correlation or not. So technically we do 3 in this course. We already did 1 and now we're doing the other 2. There's also one for standard deviation. There's a goodness of fit. I'm trying to think what else there is. Can't remember any more off the top of my head. There's quite a bit of them. Two ways. First is the critical value approach. This is done by hand. Your first step is to state the null hypothesis, which is always going to be of the form your population mean mu equals some value mu naught. Right, so null hypothesis. The average of test 2 of all the statistics courses this semester was 70. Step 2 is to state the alternative hypothesis. And there are 3 of them. It's going to be in one of 3 forms. Either mu naught does not equal that value, or I'm sorry, mu does not equal that value. This is a two-tailed test. Or the true mean is larger than mu naught. This is a right-tailed test. Or mu is smaller than mu naught. Right? So the population mean, the actual mean is actually smaller than the stated mean. This is a left-tailed test. And it's very easy to determine what tailed test it is. The inequality sign points in the direction. Right? Greater than points to the right, so it's a right-tailed. Less than points to the left, it's a left-tailed. And not equals, you can also think of it as a greater than, less than together. So it points in both directions. So your alternative determines your rejection region. You want to determine what your significance level is. You want to state your significance level, alpha. Right. The 3 most common values, 10%, 5%, and 1%, with the most common being 5%. Next, you want to determine when we're going to reject the null. All right, so that's the rejection region. At this point, you branch. Remember when we were doing confidence intervals for population mean? What were the two scenarios we had? Either we know the population standard deviation or we don't. It's sigma, yeah, that's sigma. Right? Way more likely we're not going to know it. If we do know it, these are the rejection regions. Right, Z is larger than alpha over 2 or smaller than. That's not right.
Minus 3 alpha.
Should be negative Z.
How many steps are there?
7,
Oh, 7.
I think. All right, well, 7 that she gives.
So it's actually more.
No,
Still.
I never used 7. It was always less.
Oh, really?
Because a lot of these I just skipped. I can tell you which ones I skipped. So I skipped step 3. I never stated it. I stated in my conclusion. That's how I learned it. I skipped this step. Never stated the rejection region. It was always just applied. What do I know? If your population standard deviation is unknown, these are rejection regions, again, fixed. That should be T less than negative T alpha over 2. Right-tailed, your score is greater than the critical value. Left-tailed, your score is less than the critical value. Again, those should be negatives in the left-tailed. I actually think that's a mistake in the notes that are posted online. I don't remember if I saw negatives in those or not.
Oh, so these are not your notes.
No, I just write the slides based on the textbook.
Okay.
And I do that to try and keep everything kind of, the same. Because a lot of the notation that is used in your textbook is not the notation I use. Well, once you've determined the rejection region, you now want to calculate your test statistic. Right? It's either going to be a z-score or a t-score, depending on whether you know the population standard deviation or not. Then your method converges again. And that's the only time that's the only area it branches off. Determining your rejection region and calculating test statistics. That depends on if you know sigma or not. But now it's time to state your conclusion. Determine if the test statistic is in the critical region, the rejection region, and then clearly, in words, state your conclusion. Go back. That was back. Oops. Spin 1 second. Math person, I'm very literal. It is the stating of the conclusion that most students get wrong. So let's say that our test statistic does not fall in the rejection region. That means we're not rejecting H0, the null. You would say there's not enough evidence to reject, and then whatever the null hypothesis is. You never say the null hypothesis is confirmed or true. Because you can't know that for certain. Right. Statisticians are assholes. You never want to admit you're right. We'll just say, well, we couldn't prove you were wrong, but we're not saying you're actually right. We still think you're wrong. We just can't prove it. Another good way of thinking of it is think of how many of you are unfortunate enough to have ever had to go to court? Lucky bastards. But you're at least familiar with the court process. What are the two verdicts? Guilty or not guilty? Notice it's not innocent. It's not guilty. Because you don't know if the person's actually innocent. Not guilty simply means there wasn't enough evidence to prove guilt. Only one person knows if they're innocent, and that's the person on trial. Well, I guess if it's murder, the murder victim would also know. But they ain't speaking, so that doesn't help. Also, you don't know if you can trust their word. Who knows? They might say they were stabbed, maybe they just fell off a cliff. Don't know. But in a court scenario, your null hypothesis would be innocent. The alternative would be not innocent, meaning guilty. Well, based on the error types, our system, our justice system, is designed in such a way to minimize type 1 error. We'd much rather let a guilty person go than an innocent person in jail. Right, so that would be the type 1 error, you throw the innocent party in prison. Type 2 error would be they actually did the crime and they got off. O.J. Simpson. Who actually, I believe, admitted that he did the crime, but he can't be tried again. Well, now he's dead, but couldn't be tried again because it's double jeopardy. Can't be tried for the same crime twice. It's actually quite interesting. You can literally go out, kill someone, you're found not guilty in court of law, then you can go, as you're walking out of the court, yeah, I actually did kill the bastard. And they can't bring you up on charges for it. God, I hope you know it's this is an awful process. Been to court twice. One as a juror, thankfully got off, and one, my girlfriend had an accident, so I had to go to court. Went to court with her. I never had to stand trial. So that is the critical value approach, and like I said, that is done by hand. Yeah, that approach is never actually used in the real world. The other approach is called the p-value approach. Starts off the same. So you start, I go back. Steps 1, 2, and 3 you can kind of think of as the introduction to your test. Where you're kind of stating, okay, here's the null hypothesis, here's what we're testing, here's the significance level we're using. That's like the introduction. Four and 5 would be the body of your test. Right, that's when you're actually calculating your value and determining the rejection region. I guess step 4 would technically also be the introduction. If you want to state when you're going to reject it, you can consider that to be the introduction as well. 5 would be the body. And then 6 and 7 would be your conclusion. So first 3 steps are the same. Still the introduction. State your null hypothesis. State your alternative. Right, 3 of them. Either two-tailed, right-tailed, or left-tailed.
It's all the same?
And state alpha. These steps are.
Okay.
This is where the progress comes from.
Part of it, because you also have to do confidence intervals, which is what we did last week for me. So you have confidence intervals you have to do, and then you also have to do hypothesis testing. Only for means, though. No proportions. I just looked. Then you determine your p-value. This is done using technology. The p-value represents the probability of your statistic being in the rejection region. You then compare it to alpha, your significance level. I may have misspoke. P-value of rejection agent. No, it can't be. Using this notation, I can tell you what I interpret it as. Oh, that's right. The p-value is the probability that that test statistic occurred by random chance. It didn't occur by random chance. The smaller it is, the more unlikely it is. Right, so the smaller your p-value, the more unlikely it was just a coincidence. Yes, it's the probability of obtaining your observed results. So again, the smaller it is, the less likely that you would obtain them. You reject the null whenever p is less than or equal to your significance level. And again, standard significance level is 0.05. So if your p-value would be 0.05 or smaller, you would reject the null. Meaning it wasn't a coincidence. And step 6, state your conclusion clearly in words. Again, being aware that you never say the null hypothesis is true. You say that you fail to reject it or re-reject it. And typically you do it in such a way, there is significant evidence to reject the null, there is significant evidence to not reject it, or there is not significant evidence to reject it. Something along those lines. Come back at 7:30.
I had a good night shift, so that's what I was celebrating.
We want to test whether the mean GPA of students in American colleges is different from 2.0. All we want to do here is state H naught and HA. So mu equals 2.0, or if you want to use words, the mean GPA of students in American colleges is 2.0. That's a mu.
State H O and H A.
The alternative, what are we testing?
So the H O is the alternative,
No, H naught is the null,
We're testing it.
or the, and the H A
is our alternative.
okay.
Out of the 4.0.
H has to be H.
Different from, so does not equal.
So there, this one is the two tails, right?
This would be a two-tailed test. That's all they wanted for that problem. And just state the null and alternative. Want to test if college students take less than 5 years to graduate from college on average. So what's the null?
5, 0.05.
What's null? Remember, null is always equals.
What does this?
Equals 5.
Yeah, I just said 0.5.
Null is always equals.
Okay.
What is the alternative?
This is 0.
Is equal to
What was it? Less than 5.
yeah, that's his name.
Oh.
So this one we don't have to do like 0.05.
No, we're not doing the actual test here. We're just stating the hypotheses.
Okay. Got you. Now Yeah, those were the things we were talking about, right? We still don't give us the questions. Okay?
In an issue of U.S. News and World Report, article on school standards stated that about half of all students in France, Germany, and Israel take advanced placement exams, and a third of them pass. Same article stated that 6.6% of U.S. students take advanced placement tests, advanced placement exams, and 4.4% pass. Oh dear. That is not good. Test that the percentage of U.S. students who take advanced placement exams is more than 6.6%.
This one's a little different.
What equals?
No.
We,
Oh, yeah.
This is not mu.
that's the T. T. What's this percentage? It's not a percentage.
This one is actually testing proportion. We're not going to actually perform the test, so there's nothing wrong with at least throwing it up there.
So what is there any way we can figure out there's what I written within there that we can see and let's just know that it's proportion.
Yeah, 6.6%.
1.6%.
That's a proportion.
Okay.
Unless it's set on average.
I'm glad you
Then that
understood
would've
my
been
question.
average.
Thank you, yeah. I see that's how you know the difference.
What would the alternative be?
Like less than 4.4.
More than.
More than
It should be
six.
more, yeah.
1.6.
Yeah, this one is P is greater than
It's more than 6.
0.066. So the value for your null and your alternative will always be the same. All that's changing is the sign.
Okay.
Is it equality? So null always equals, alternative will either be not equals, less than, or greater than, depending on what you're trying to test. Certain experimental drug claims a cure rate of at least 75% for males with prostate cancer.
Wow.
Reaching that age.
No.
The blue glove of doom. Describe both type 1 and type 2 errors in context. Which error is more serious?
Wouldn't it be equal to? Well, type 2 is more serious.
So remember what a type 1 error was.
That's correct, right? That's when, it's true, and type two is when it's not true.
It's accepted,
Reject.
rejected, and when it's false,
So type 1 is rejecting the null when it's true.
True.
just have type 1 and type 2 different. Oh no, I messed that up. I just messed up my word.
We really know we mess up or not.
Yeah, I swear we wouldn't know.
Rejecting H naught. H naught is at least 75%. So it'd be less than. At least 75%, so 75 or larger. So then the alternative would be less than. So when you reject the null, you assume the alternative is true. In this case, less than. All right, type 2 is failing to reject. Right, so you don't reject the null. So you believe the cure rate is 75% when actually the alternative is true. It is less than 75%. And then which one is the more serious error to be made?
I see two, the two statement, 187, it's less than,
Hmm?
The first one.
First one?
but it should be less than 7.
Second one.
So that's more true.
Right, you take a drug and you believe that the cure rate is less than it actually is. That's actually really good. That means you have a better chance than what you believe. Type 2 in this case would be you have a smaller chance than you believe. Right, so it'd be like you go in for surgery believing that it's a 99% survival, and it's actually a 20% survival. Right, you would never agree to the surgery if you only had a 20% chance of surviving it. Well, that's not true. I guess it could be if you don't have the surgery, you only have a 1% chance of survival, then I would take a 20% chance of surviving the surgery versus I'm basically guaranteed to die if I don't. God. Okay, one of these types of problems where
All these
the
bonus.
entire slide. Jeffrey, as an 8-year-old, established a mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad thought that Jeffrey could swim the 25-yard faster using goggles. So Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, mean time was 16 seconds. Frank thought that the goggles helped Jeffrey to swim faster than the 16.43. Conduct hypothesis test using significance level of 0.05. to test whether it is true, whether that's the right conclusion. Assume that the swim times for the 25-yard freestyle are normal. That's important. Because it's normally distributed, we can perform the test. If it wasn't normally distributed, we'd have to have at least a sample size of 30, which in this case we don't. Do we know the population standard deviation? 0.8. We do happen to know in this case, 0.8. So this is going to be a z-test, not a t-test. What's the null?
Of the question you just read,
What's the null hypothesis for this test? What about 16.43?
mean times
Because it's the,
the mean, yeah. So it's
because
16 point,
it gives it to you. That's
the
not
mean
the
times
shooting.
16 point,
Equals, right? Mean equals 16.43 seconds. What is the alternative? Greater than?
16.4. It's actually lower than.
Less than.
Yeah, because that's more time.
Faster means you swim it in less time.
Yeah, less time is faster. The more time it is, the slower you go. That's like me and you having a race.
It takes you an hour to get to the grocery store, half an hour to get to the grocery store.
And then
Where
only
did you
took
get there?
15
the
minutes.
faster
Sometimes I
you
got
put it,
faster.
less time.
You get it now?
Yeah, I get it.
So this is what kind of tail?
Like two tail.
Which side?
Yeah,
Left.
Left side.
Left side.
Don't know.
It's left.
I'm opposite of what you're doing.
That's a left,
That's my right.
that's a left. Once it's
This is a left tail test.
Once it's left,
What was the second step? The first was, oh, I did the second step, that's right. To state the alternative,
State the alternative hypothesis.
which we just did.
Mhm.
Third step was to state the significance level.
It's 0.05 rate.
Here's the good news about these. You don't actually have to write this into your report yet.
yeah.
Yeah.
Whenever you're actually doing it as an experiment, you do. When you finish the hypothesis test, you have to write that in a report form. Any kind of experiment. It's always written to a report form. So if you had to submit this report, you'd have to actually write it out as a report.
Oh, wow.
Have you done that before?
Sucks. I just hate writing papers in general, so that's why I'm not a researcher. That's why I'm a theoretician.
So for step 4, we already determined the rejection of this left tail.
Right, so we have to actually physically state. So since we are looking at one-tailed, this really should be in there. State Z alpha, state the critical value. Need our chart.
Which one is that, a C or a B?
We want to find the z-score that has 0.05 area to the left. The critical value will be the absolute value of that. I'm looking at 0.00. Oh, God. That's not what I want. Is oh, I don't see your charts. I want the critical value. $1.645.
Mm-hmm. Oh, that is 90%.
Right, that would be if it was a 9% confidence interval. We're not doing confidence intervals, we're doing hypothesis testing. And it's a one-tailed test, so it's not alpha over 2, it's alpha. The rejection region
Reject if C is less.
Really long contagious.
because it's left tail to reject when our test score is less than negative the critical value. Now we have to calculate the z-score. Sample mean is what?
16.43.
Yeah. That's the standard
That's the
deviation.
standard deviation.
0.05, 16.
16 is the sample mean.
In the meantime.
Minus population mean. Divided by population standard deviation divided by square root of our sample size. Because remember, since it's x bar, you're looking for the mean of the mean distribution and the standard deviation of the mean distribution. Key value, you suck. negative 2.08. Is that in the rejection region?
So, negative 2.08, would that be facing more towards the right or the left side?
That's what I'm asking. Is that in the rejection region?
Yeah.
That is less than
It's
negative
one.
1.645. Which means we reject the null hypothesis. We now need to state the conclusion.
Okay.
Was it 25 yards? There's significant evidence at the 0.05 significance level that Jeffrey's mean time to swim that 25-yard freestyle was less than 16.43 seconds. Which means the father, we're not going to say was correct. We have evidence to support his claim that Jeffrey swam faster with the goggles. Right, so the father didn't draw an incorrect conclusion. Notice the wording. It never actually says for certain that his mean time is less than 16.43 seconds. It just says there's significant evidence. Right, so the evidence shows that he did indeed swim faster. For the p-value method, I'm not going to redo the whole thing. You don't need Z of alpha anymore. You'd still need these, right? H naught, HA, and alpha. Then we'd have to find a p-value. Stat tests. Because we knew sigma, this was a Z test. What is mu naught? What was the standard deviation of the population? Mu naught is 16.43. Standard deviation was 0.8. What was the sample mean? And what was the sample size? And then what kind of test are we looking at? Less than, right?
Oh, so you don't push data first?
No, that is going to be if you want a list of data that you're using.
Oh, okay.
It actually does give us the z-score, which is nice. There's the p-value. Which is the area to the left of negative 2.08. So what you would do, and yeah, I'm not going to actually do it. You would then write down, after you listed out your H naught, your HA, and your alpha, you then say P is 0.0187, whatever. Now you have to look at that. Is that smaller than alpha? So is that less than alpha? So you state that it's less than alpha. What's your conclusion? It's the same thing. If P is less than or equal to alpha, you reject the null, which means there is significant evidence to support the alternative. You would lose points if you somehow stated for certainty that one of the hypotheses was true. Right? Because you can never be absolutely certain.
So you always gotta be.
Right. It's only
certain.
right. There's only evidence to support.
It's either there is evidence or there is not enough evidence.
Right. So again, it's you either reject the null or fail to reject the null. Never say it's actually true. Same thing with the alternative. If you want to state it in terms of the alternative, you would never say the alternative is actually true. You would just say that there is significant evidence to support it, or there is insufficient evidence to support it. Which is to say you can say that's wrong. You're allowed to say that. Remember, we're assholes. We love to call you an idiot when you're wrong. But we'll never admit that you're right. Good to say it's kind of the definition of a wife. They just walk away when they're wrong, and they won't ever say that they're wrong. And then the husband has to apologize.
So you're saying there's no accountability in statistics?
Well, I mean, maybe not in statistics, but you're the person who's using that statistics, and then it costs lives, you get held accountable. Unless you're in government, then you don't. Like those engineers that killed 4 astronauts because they were stupid and didn't convert their units. Nothing happened to them. Yes, of course, another freaking long one. Oh, lovely.
God damn.
This gives data too. This is freaking perfect.
Do you have to add all these numbers? All these figures?
Unfortunately.
Telling me that you got data range from 205 pounds to 3 pounds. You gotta put it in order. That is 1, that is 2, 3, another 2, 2, 2, 1, 1, 1. Okay.
Okay? Yeah, I'm not reading that whole thing. Time for that. First, we want the null. So what is the null hypothesis? What's 275?
No, that's the mean.
So mu equals 75 pounds.
So it's- But that's still the mean though, right? Okay. Yes, sir.
What's the alternative?
Greater than.
Oh, mean white.
Yeah, there's a lot of typos in there.
That's how it'd be like on a quiz.
Okay. At least my excuse is this disconnects on me a lot. This keyboard doesn't, it resets everything you won't type. It's so
Oh yeah, everybody, I got y'all 100 on whatever quizzes. No, I'm dead serious. I got y'all all 100 on the quiz. Remember I was pointing out all the mistakes. You did
What is the significance level? Put that as a decimal. One of those unusual ones. Of course. Good news. We don't need to find the critical value. Because I'm going to be doing the p-value method using technology. Bad news, unless you have the calculator I recommend, you have to actually calculate the sample mean. It's not given to you. Is sigma known? Do we know the population standard deviation? We do know it. So this is a z-test, not a t-test.
And how would you know it? No.
Really just not spelled weight at all right. This is why I'm not an English major. I think I got them all. Can we do a hypothesis test for this? I should have did that before starting.
Yeah, all of them together. And
So
get
can
the
we
mean.
do a hypothesis test?
Yes.
Yes, why?
Because it's saying conduct the hypothesis test.
No.
Using the tool.
I could ask you to do it and it's impossible.
Oh.
Just to see if you were actually paying attention. Thank you. I agree. Way too long. Again, it is not freezing. Freezing is 32 Fahrenheit. It's 76.4 Fahrenheit. Not even close to freezing.
It's hot in the zero.
So what are the conditions that have to be satisfied to perform the hypothesis test? Central limit theorem. Either the population is normally distributed or what?
Above.
Hmm?
Above 20.
Not 20. 30 or larger.
Yeah, that's the way to be.
Is our sample size, so first off, is our population normal?
The population.
Is it?
Yeah.
Yeah, yeah,
Doesn't say if the population is normal or not.
nothing was sure.
But if you think about it, teammates, it wouldn't be.
They asked 30 of the team.
That's why you then have to look at the sample size. Sample size is 30, so it doesn't matter. So yes, we can perform a hypothesis test. If we already knew the population was normal, the sample size doesn't matter. So we can perform the hypothesis test. feel like calculating the mean myself.
No. That's how we feel when we have such numbers.
I'm going to create a new list and enter my data. I think I can. I love UTI Inspire.
What did you just do?
Same thing I can do on Excel.
Um,
Drag and drop to re-enter data.
how do you drag and drop?
It's going to be a little bit harder with the
Like the
handheld
actual calculator. Right.
because you have to use the center as a mouse pad.
Oh yeah, that's what.
So it's a little bit more difficult, but you can do it. This is only 2, so it's easier to do that. 252, 275. Looks like they put this in ascending order as well. Oh god, there's 5 of these. 5. 2 338s. 341. 2 of these.
2041.
2 of these. And a 385. I'm missing one.
Five.
Where's 316?
We have 3,
1,
6,
2, 3. What happened? Did I overwrite one? You bugger. Insert row. Ha ha! Victory's mine. I win. You lose. 30. Perfect. I'm going to title that L1. Guess I can title it whatever I want, so
You can write whatever.
wait. Menu, statistics, tests,
Zeta.
z-test, using data. Mu naught, sigma, 55. List, weight, frequency, I'm just going to use 1. And we were doing
mode.
greater. And where do I want the results to go? Yeah, that's fine. P is fine. I don't care. Do I want to shape p-value? Yeah, sure, why not? Let's
What
see
is
what.
that?
I have no idea. Let's see what that option gives us. Because I really don't know. I've never done this. When I did hypothesis testings, we didn't have these fancy calculators. Cool, it gives me the graph! Oh, that's so cool. I thought that's what it would be.
So it's showing that it's oh no.
Oh, that is so cool. The problem is,
So we're gonna have this in the project too, the graph.
I don't know what the project's asking for. And so the problem is now, of course, that graph is kind of messing everything up. And all these are kind of, why is it, oh,
I see a lot of.
because this goddamn title. You know what? You can just go away. And then can I resize you?
We're not gonna be on next week.
No, I can't.
You may have to go back and unshade it.
Whatever.
So we're gonna see what-
P-value, this is the one I want right here.
Row 4.
still see.
So let me highlight that. So p-value of 0.1345. How does that compare to alpha? So what is the conclusion? Do we reject the null or not?
It will reject.
Hmm?
It will not reject.
Let me see.
So it's kind of slow, but
It's better.
So what was the rule for p-value?
we reject.
You reject the null when p is what compared to alpha? Less than or equal?
I think
Is this less than or equal?
It's great.
Look,
So we
here.
fail to reject the null.
Oh, here's less now. So what was that? What was the last one? I don't know. Yes, so it's better.
We have insignificant evidence to support the claim that the mean weight lifted is larger than 275 pounds.
It's stressful. It's not even good for you. It's not that.
See that?
Yeah.
By the way, you can be here for 35 more minutes if you want, but you're going to be very lonely. Oh, you don't you dare do that to me. You suck.
Oh, we're not gonna talk about the project?
Well, I'm not done yet.
Oh.
Did it stink again or didn't want to save what I wrote?
I never used to hear.
It's down this Yeah,
Oh my God.
right next to the vendor's machine.
Okay. I don't know.
Once you see the machine,
And then it's right there. Okay, thank you.
we're gonna link over till you see the machine.
Thank you.
So can we perform a hypothesis test here?
10 simplest less than 30.
We can. Why? That are assumed to be from a normal distribution. So we can do it. Do we know the population standard deviation? No, that means this is a t-test.
Oh, so when you don't know the standard deviations.
So it's
Okay.
unknown.
Yep. So this is a t-test.
T is unknown. C is unknown.
What's the null?
And no equal 65.
What? About 65.
No equal
Mu equals 65.
65.
Then what is the alternative? Mu is
It's greater than 65.
Yeah.
greater than 65. The instructor thinks it's larger.
Yeah, it's higher.
All right, we're going to perform at a 5% significance level. So what's alpha?
Alpha
0.1.
is
Zero.
No,
0. 1. No?
0.01 minus 0.005.
Oh, 5. Oh, yeah.
0.05,
Because the
5%.
hypothesis 5%. Yeah, done.
Is this a one-tailed or two-tailed?
That's a
Shouldn't it be 1?
Which side, left or right?
It's
It's,
greater than, so.
this, right.
It's a right-tailed test.
So it should be right.
So we need T sub alpha.
Professor, sorry. Actually, so to find the alpha, you have to subtract 1 minus the
Confidence level.
That's confidence. This
So-
is hypothesis.
so it-
They're giving us what the significance level is already.
Yeah, it's the 5%.
also this is not the confidence level.
No, this is not confidence level. So the confidence level is 95%.
Yeah.
Significance level is 5%.
90.
Oh, I get it.
Oh,
Thank you.
significant.
So we have to come over to our student T table. What is the sample size?
Yeah. I put 10, I forgot.
Which means we have how many degree of freedom?
What did he say? I'm sorry.
What was it? 9. Degree of freedom is 9. So we want, with degree freedom 9,
It's the next 10.
we want area in the right tail to be 0.05. 1.833 from the table.
That's not the 2. Yeah, that's what I'm saying.
When do we reject the null?
You check the no.
We reject when
But it's
it's
true.
when it's greater than the
Reject if T is greater than T sub alpha. Now we have to find t. Unfortunately, that means we have to find the mean and the standard deviation. So for the sake of brevity, I entered the data to my chart. Come down here. It's probably the statistics, stat calculations, one variable statistics. Right, I want D. What's this? Cancel. Okay, so that's apparently not what I wanted. Oh, it actually gives me everything I want. Okay, that's nice. So there's the mean. 67.
Okay.
And here is the standard deviation. For the sample, you want SX.
So, say for the people who don't have the calculator, how would they find it?
Using the formula for standard deviation, which was way back in week 2. Or hope that I'm nice enough to give it. Although I think the 83 and 84 has lists. So you might be able to do it on the 83 and 84. If you have a scientific, you're just screwed. You can't do it. So I'm just going to write down my X bar was 67, and my standard deviation how far out do I want to go? Maybe we'll just drop to 3, 3.197. That sounds good. I'm also showing you how to do this by hand because it's a t-test. I'm also going to show you how to do it with technology. We need to calculate our test statistic T. X bar minus mu, which is 65, over sample standard deviation. We said it was what, 3.197 divided by the square root of the sample size, which is 10. .98. or 1.978 if you want to go up to 3. I think I will because the table gives 3 decimals. So 1.978, let's say. What was T alpha? How does it compare? So do we reject? Reject H naught. I'm going to say sufficient evidence. So we have sufficient evidence to support our claim that the average score was indeed greater than 65. So same process, just a different test statistic. It's T instead of Z. Back over here. Menu, statistics, stat tests. This time we want the t-test. Right, you're again going to have 2 methods, data or the statistics. I already have the data, so I'm just going to use data. List out mu naught, 65. My list was actually D. It was greater, right?
Yeah, it was great.
And show results in G, and I'm not going to do the shade T value this time. There's the p-value. How's that compared to our alpha? It's less than, so conclusion, reject the null. Because p is less than alpha. And then you have the same conclusion as we just did. See that? Questions on hypothesis testing?